Hello, everybody. Good afternoon. My name is Jonas Bien, and I would like to welcome you all to today's online training. This is the first part of our series RFEM 6 for students, and we will today talk about member design and about the basics of modeling and results interpretation and so on. So I hope you all can hear me very clearly, can see me in my webcam, and also see the screen that I shared. You should see the first slide of my PowerPoint presentation by now. Yeah, I'm Jonas Bien. I'm working at Dlubal Software for now half a year almost, and I'm responsible for product engineering in the field of steel design and also in customer support. I'm today accompanied by my colleague Richard Hase. He will follow the webinar as well and stay by the side to answer questions that you might have during the webinar. But maybe he can introduce himself just very quickly, himself.
Yeah, hi, I'm Richard, and I will assist Jonas today and will chat with you. If you have a question, I will answer this. And yeah, okay.
All right, so then I would deactivate my webcam so you have a bigger portion of the screen for what I will show you. And before we go into the overview and what we will talk about today, some basic functions of the GoToWebinar control panel. So on the right of your screen, you should have a control panel that you can show and hide by clicking this orange arrow. Here you can adjust your audio settings and also, which is probably most important, you can enter questions in this small chat box here. The questions will directly go to Richard and he will try to answer them as best as possible. If the question is a bit too complicated for today, or it's too late to answer it at the end of the webinar, sometimes they merge up all these questions, then you have also the possibility and that you have at all time to just contact us by email, writing it to info@dlubal.com. All right. So as I said, today's event is one within the series RFEM 6 for students, and this is the first event. We will deal with member design today, but I want to make you aware that there are following events starting next week, the week after, and so on. And if you are interested in those, definitely check out the topics that are handled here, and just apply for it. And this is probably quite interesting depending on where you are in your studies. So the first 3 events are basics, and the last 3 events they deal with real design, material design, reinforced concrete design, timber design, and steel design. All right, RFEM 6 is a 3D structural design software. I don't know how many of you have already worked with it. But it can be used for many different applications. It's rooted in civil engineering, but also can be used for mechanical engineering or special applications. And it can be used to design with members, shells, planes, and also volume elements. But today we will focus on the members, on the simplest element of all. All right. So the content for today is the introduction to RFEM. We try to get used to the user interface first. I want to show you the different areas that we have on our user interface and how we can interact with the program. Secondly, we go through an introductory example, a very easy one, a single span beam. And then we have numerous advanced analysis examples that are mostly static. And then in the end, we will explore a bit the possibilities of higher order theories like explore the influence of second order theory and how you can take care of this within RFEM. And then we will also do a small and easy example for a linear bifurcation or stability analysis. You have the chance, if you would like, you could work along with me. So if you have the possibility and if you are interested in it, you can open RFEM and also click with me through at least the first examples. There I will do it very slowly, so you have the chance to do the same thing similar and ask questions if you don't understand, if you have problems understanding something. So maybe in order to also define my speed, I would like to ask you one question here. If you are interested in working with RFEM during this training or not, you always have the chance after this webinar to download the video via YouTube, so it will be published there. So you could also do it afterwards. But yeah, just a short introductory question also to improve interactivity. So there will be a few of those questions that you should now see on your screen during this webinar. All right. So I've seen a lot of you have already answered, so I will close the poll and show the results to you. So yeah, it's very even. So a few of you or some of you would like to work with RFEM besides my presentation. So I will definitely start a bit slower. And as the topics get more advanced, I will probably speed up a little bit. All right. So let's dive into the program. And yeah, first of all, I want to show you the user interface. It's broken up into different parts. So we have the menu bar, toolbar, view cube, workspace, table, status bar, and navigator. It's probably best explained directly in the program, so I will just jump right into it. Here I have a little demo model that you have also available in the Dlubal Center, but it's just for demonstration purposes. So just to show you how the user interface looks. Yes. You have. Yeah. Sorry. Okay. Sorry for that. It's still the poll shown to you. All right. So I now jump into the program, and what you can see here, this is the user interface that you will be working with in RFEM and also in RSTAB, RSTAB, which is a very similar tool, but this is just focused on member design. In RFEM, you can also design with 2D and 3D elements, and it has the same functionality when it comes to member design. So this is the more general software kit. So, but everything I'm explaining here to the user interface is also valid for RSTAB. So at the top, we have our menu bar. Here we can open, edit files. We have almost every function we can use in this program, we can access via our menu bar. However, it's quite inconvenient to browse through different drop-down menus and so on if we want to just insert a note or a line or a member. So mostly for modeling and assessing results, you will be using the navigator or the toolbar. This toolbar is highly customizable, so you can add functions to it or take some away that you never need for your purposes. The menu bar is mostly interesting when it comes to tools. This is used quite often. Here you can do model checks, plausibility checks. This is this is uniquely accessible through here. And also the options, that's where I also use the menu bar a lot. So Under options, you find the display properties. This is quite important. You can customize almost everything from color to fonts to font sizes and so on. Maybe you are already wondering why I have a wide screen. So this can be, for example, very easily changed. You can just change your background color here, or we have also, I think, a quick switch option here at the bottom. If you prefer to work with a white background, you can just very easily do this, set the white background here. And you can, of course, save all your settings, your display properties in a template and load it for other projects or new installations. Another thing that might be interesting to you, I don't know where you are all coming from, but under program options, you can set the program language. You have several possibilities. If you switch the language, you have to restart the program. But yeah, it's quite easily done here. Another important thing maybe also depends where you are working with the software. You can change units and the decimals also under this options, units and decimal places. You can also assess these options in the table here, but there you can customize every unit and also the decimal places that it's shown for almost everything that is shown in the program. Yeah, as I said, the toolbar is highly customizable. This one here, just below the menu bar, this is quite convenient to use for most modeling options, and also to quickly, for example, show loads and hide them, or show results and hide them. You can have also some quick options for views that are preset. For this, you can also, which is now in RFEM 6 quite nice, you also have this view cube where you can select edges or corners, or you can also drag and drop the cube to seamlessly interact with the view. Then you have the option to change the display settings here quickly. So you can go from wire model, where just the middle surfaces or lines are shown of the objects, to the solid rendering or the transparent solid rendering option. So this is quite often used. And yeah, just here below are all the modeling settings. Here you can define most of the objects quite quickly. All right, on the left side, we have the navigator. This is, I would say, essential to keep track of your model. So under the navigator, this is the first navigator tab. It's navigator data. So you have 4 different navigators, as you can see here at the bottom. You can switch between them. And in the data tab, you can keep track of all the objects you have defined in your model. For example, all the materials that I have defined for this model here, the sections, nodes, everything is displayed here and easily accessible. And if you click on one of those objects, you can see all the related objects in the workspace immediately highlighted. So if I click on this material, I see all the objects that have this property, this material property. Same goes, of course, for the sections and so on. Besides the basic objects, there are also types for these basic objects. So these are modifications that you can perform on these basic objects, and several other topics that you can treat here, like load cases, generation of design situations, and so on. So the navigator is very convenient to work with for most part. or it's nice to work with it along with the toolbar, because here you can keep track of everything that you defined. Same goes also for the table. Below here, you also have a nice overview of all the objects you have defined. It's the same structure as in the navigator, in the data navigator. You can also find here different sections that you can show in the structures, like the folders up here, basic objects, special objects, types for notes, and so on. You can also assess here. It's just that you have to find the specific table that you want to display, while in the navigator you can see many different information at once. But this table might be nice to use. For example, you can directly input values here and change. For example, if I go to the nodes, I can directly change the position of a certain node here in this table. Whereas through the other options, I would need to open some dialog and so on. So this might be convenient for some operations. And also a nice feature is you can export all these table information to an Excel file, manipulate it there with all the functionality that you have in Excel, and export it again to RFEM. So this can also be a nice use for this table information. All right. The navigator has then 3 other tabs. One is the display tab, where you can show and hide different objects, or you can change the view settings. For example, I can hide all members or all nodes if I want so, and you can do this for very particular objects. You find here the settings to view and hide all of these. So if you are at some point missing some objects in your workspace, it could be that they are somehow deactivated here in the display navigator. Then we have the views navigator. Here we can define object selections. For example, we can select all the beams at a certain floor, and we can then quickly assess them, or we have some predefined filters here. So we could, for example, very easily filter by a member section, and then just activate in our active view the members that have this certain section or a certain beam type, element type, or whatever. So this is very nice if you have complex models with with a large amount of elements, and you want to keep track of them, or want to edit a certain group of objects. This is nice to just pre-select them and then select all of those objects that you want to manipulate. And then if you have calculated, or if you already ran some simulation, you can find also the tab results, the navigator results tab. And here you can assess all results that are available through your simulations. In the basic structural analysis, you get deformations, internal forces, stresses, strains, support reactions. But that very much depends on your calculation settings and the objects that you are calculating. All right, then maybe some important features like how you can manipulate your view or select objects with your mouse. You with the left mouse, you can select an object. You can also hover. If you hover over an object, you get like such tooltip with quick information already. But if you then double click on it, it opens the edit dialog for this object. And if you want to just select it, you just click it once. You can add objects to the selection by holding the Control key. So that's in the lower left corner of your keyboard. Then you see a little plus sign over the cursor. and that indicates that if you click now another object, this is added to your selection. If you instead press the Shift key, a little minus appears and you can deselect objects from your selection. You can also select multiple objects by drawing a rectangle or open a window, left click and draw your mouse somewhere. I will quickly just activate all my elements in the visibility mode so I can show it to you. And there is a difference whether you create this window from clicking left to right, then you get a yellow window, and that means that only objects that are fully in this window will be selected. So if I just release my left mouse button now, it will just select the two nodes and the supports. If I instead draw my window from right to left, then it will it also changes the color. I get a blue selection window, and it will select all the objects that are in touch with this rectangular window. So it will also select the two columns over the supports. Yeah, this is very, very important. Then you have the middle mouse button. If you just you can use it, of course, for zooming very intuitively. If you scroll on it, you can press it to pan your model from left to right or up and down. Then you can hold your control or alternate button on your keyboard and press your middle mouse button to change the viewing angle. And if you double tap on the middle mouse button, it will auto fit your model in the workspace. So these are some, the middle mouse button is very important to navigate your view. So if you are working right here and have done some modeling, you changed, for example, the support conditions, then you double tap the middle mouse button and you get the whole model again. All right, on the then on the right mouse button, you can use it to also draw a window for zooming this time. So if you release it, it will zoom the area that you just highlighted with this window. And if you just click the right mouse button somewhere on the workspace, you will get a context menu where you can quickly change some settings. And if you right click an object, you will also get some specific controls or some specific functions that are special for this object that you selected with the right click. So I could now, if I right click on the support, I get some functions that are made for these supports. I could, for example, at this point very easily change the size of these supports for viewing. All right, I think this is these are the most important functions. You can just play around a bit with it to navigate through the workspace. Just try different combinations. You have a lot of shortcuts that you can also check out here in the customize toolbars. You can check a lot of those shortcuts, might be interesting to you. All right, but I would say this is enough of an introduction to the user interface. Now I would like to start with the modeling and simulation work chapter, so to say. And as I said, if you want to work with me along, you can now, I would say I just close this model. I won't change any I won't save any changes. And then I just quickly open a new model. I can do that via the toolbar or via File and New. Then I get a dialog for a new model. I can assign certain project to the model that I want to create. For example, I have one project folder for my trainings, and then I just create a new model. Let's say I name it now single span beam, because that's the first example that we want to generate. We can then, I think this is mostly convenient, or it's easier maybe a bit to work in the 2D space. So we will reduce the number of degrees of freedom and take some complexity away. Also, you have in this base data dialog the option to switch add-ons and or activate or deactivate add-ons that you may, for example, need for the design of certain members. So if you want to do concrete design or steel design, you find the design add-ons here on the right, but there are several other analysis add-ons that you can activate or deactivate, but these are mostly for advanced topics, so we will only use one later. This is structure stability, but then I will show you how to activate it again. We also have the option to use combination wizards and classification and load wizards to make it a bit easier to perform all the combination of load cases. But we won't need that in the first step, so I will just deactivate it. And then I will create this new model by clicking OK. So before we start to model, maybe I show you our the aim of this first exercise. So we want to create a single span beam with a concentrated load. The single span beam will be 7.5 meters long, and we want to apply a single or concentrated load in vertical direction. At some point, not at exactly at the middle, but 4.5 meters away from the left support. All right, so let's do this. I just want to change the view to the XZ plane, and if we want to create a member is always, or it's good to know that a member is always connected to a line, and a line is always connected to at least two nodes. So a line needs one node at the end, at the start of the line, and one at the end of the line. So in this example, we will go through this hierarchy and first define nodes, then we will define a line between these nodes, and then we define a member on this line. To not spoiler anything, I will delete all my basic objects. So this is empty, so I have no predefined materials sections or whatever, and start from scratch. We can, for example, use the toolbar to create a new node. This would be this button here. And then we also have several possibilities to create this node. We can go in the workspace window and directly create a node by clicking at some location. As you can see, when I move with my cursor through this work plane, there is a standard grid defined with grid points that are have a spacing of 1 meter. So I could conveniently use these to define the nodes, or I could, for example, use this input dialog to define it. That is what I want to do in the first step. We want to try different methods throughout this webinar. But yes, I can just enter the coordinates where I want to create the node. One will be in the origin of our workspace. I click apply if I'm satisfied with the coordinates, and then the second node will be 7.5 meters in X direction. So I will enter 7.5 meters and hit the apply button again to create the second node. As we can clearly see the second node that has been generated, but the first one is somehow hidden between this coordinate system. So I will directly show you how to hide this. I mean, we have also this interactive coordinate system here at the bottom left of our workspace. So I think this is enough to see where how the global coordinate system is positioned and oriented. So we could go through to the display navigator tab, then to general access systems, and hide the global coordinate system. Let's see the full description. So this would be the option to hide or activate or deactivate the global coordinate system in 0 point or in the origin of our workspace. And if I just untick this checkbox, it will disappear or be hidden. And now we can see our first node that we defined as we wanted. All right, the second step would be to create our line and use the first line as our starting point, and then move to the second one as our endpoint. So I just click the first node that we defined and then the second one, and I see now we have defined a line. If I click escape, I can escape the creation or generation dialog and come back to this workspace. If I, by the way, want now define another line, so if I want to use the same function that I used before, I can just quickly press enter, and it will automatically open the last function that we used. And if we press escape, it will disappear again. So now we have nodes and a line. We can also look into our navigator here to see in our overview that we have 2 defined nodes, 1 line, and now we finally want to define our member. To do this, we can, for example, double click on the line and say, okay, this line, it has several options, and one option is that this line should have a member, should be related to some member, and as we activate this or check this box, we will be asked to edit this new member. Since we don't have defined or didn't define a section yet or a material, this is what we need to do to define our member. First, we have to choose the member type that we want to define. We have several options. For example, we can define a full beam with all 6 degrees of freedom. We can also define a rigid element that has infinite stiffness. We can define truss members and so on. But for the first example, we want to start with a member type definable stiffness. This is some more artificial member type that is not so commonly used in real design or everyday engineers design offices, but mostly since this is a training for students and we also want to show you how you can already use our programs in your studies. This is a more academic way of describing a member. So if we set up the definable stiffness member type, there's another tab here where we can directly define through numeric input our local stiffness metrics of our beam. So that would be quite convenient if we have a task with an arbitrary EY or a given bending stiffness and axial stiffness, so we could just enter them here and we wouldn't need to find like a geometry of a member that fits to our stiffnesses that we have given in our task. So we could define everything we want here. I will just now put everything to unit and press OK. So we have very low stiffness now defined for this member, but this is just for the example of how you could set up this. And if I press OK now, that should be already sufficient. We don't need any section or material to define the member properties in this case, since we directly defined the stiffnesses. So now it's barely seeable or visible that we have now also a member defined here. It's just indicated by this dotted line, which is plotted over the line. So other member types are visible a bit better. So don't worry about that. Then for a single span beam, we also need supports. We can also assess the nodal supports through the tool bar up here. And we want to assign a new nodal support. So if we click here, a new dialog opens, and we can pick a node that we want to define, or where we want to define a nodal support. And then we have a drop-down list where we can or select some predefined support conditions. We can see that, or let's maybe go. You can also create new nodal support types by clicking this button right here, or you can edit the selected nodal support. Let's just press on this one to see the options that we have for a nodal support. And we see here, these are all the degrees of freedom that we have in a 3D model. Because we have chosen to model our structure in a 2D space, some of these degrees of freedoms are great, so they are inactive. The translational movements, for example, in y direction, so out of our modeling plane, is not allowed in this case, since we just have defined our 2D model. This is also indicated in this preview here with these 6 boxes. The gray boxes, these are inactive degrees of freedoms, and the other one we can adjust. And if we want to define our support conditions, we can check the degrees of freedoms that we want to restrain. So if I check UX and UZ, that means this direction is fixed. If I could, for example, also add the rotational restraint, and then it would be this member that I defined would be clamped completely. So there are also some predefined pictograms here where you can choose the most common supports, but this is, I think, a nice overview. Okay, so we want to have this one restrained in X and Z direction, and then to have it aesthetically determined, we want to add another support here. We can also do this like manipulating the definition of the node. So I can also double click on this node, or go via my context menu, right click on it and edit this node. And I can also, just as I had the option to add the member to a line, I can here add a support to the node. And if I click it, I get this the option to assign a nodal support to this node directly. In this case, for our second node, we just want to have it supported in Z direction, so we can see in this preview, nodal support type number 4 has just a checkbox in this third, or it's just ticked in the third checkbox, which stands for the translational movement in Z direction. So this is just fine for my purpose. I can probably just, okay, on the right side, you have always the option to get a preview of the support that you define for your node. And I can see this is quite nice. I have support in Z direction, and it can slide in X direction, as indicated by this object here. And if I click OK, it's generated, and I have now my supports. Now I want to apply the load in the last step. I have two options to apply this concentrated load. I could define a concentrated load on the member, but in this case, I want to add an additional node at the point where I want to apply the load, and then apply a nodal load to this additional node. And to create generate an additional node, I can click my member and then divide my member into two or multiple parts. And I have the option to define intermediate nodes or define the division by distance, and I will do that. It's easier for me now. In my task, I've seen that the node where I want to apply my load should be 4.5 meters from the member start. So I enter 4.5 here in this box. So 4.5 meters from the first node. And if I click OK, you see this a third node is created on this member, or in the position of this member, and I have also at the same time divided my lines. So instead of one line, I now have two, and I also have two members. I could also, I will reverse my action to show you another method. I could also do the same. So divide the member by distance and create a member on, create a node on member. And the difference is that in this case, if I just create a node on member, the line and the member is actually not split. So you can see if I define this blue node here, it's a different type, and it doesn't split up the lines and the members. That can be later helpful for when you have to design such members. So you can still design this member as one continuous member, and you don't have to define two members or set up the options for the design of two members. Okay, now we also have our intermediate node. Maybe to get a feeling for the dimensions, we can now add some marking or the dimensions. We can measure the distance between the nodes to check if we did everything correctly. Up here you find the option to add a linear dimension, and I just click on the first and the second node on the member. Then I have to change the plane where my dimension is then shown, and I can do it via drag and drop, or I can add a fixed distance or an offset of my measurement. So I can define both measurements that I want to make visible here at the same height. So this is then very convenient. And yeah, that seems to fit. So I have 4.5 meters, and then I have my intermediate node 3 meters to the right support. And now the last step is to define a load. A load is always attached to a load case. There's always one load case predefined. That's by default, that's the load case number 1, self-weight. You can see it up here, or under the navigator tab in load cases, LC1. And in this load case, I now want to define a load. So you can see here how it's structured. The loads are entered depending on a load case. So for this load case, I could either go through the navigator and go to load case 1 and denote a load that I want to define in this load case, or I can select load case 1 as active load case and then use the toolbar to generate in a new nodal load. That I want to do. Choose this blue node here, the intermediate node, and then all I have to do is to enter the magnitude of my load. should be 10 kilonewtons. In the global coordinate system defined in Z direction, so that's perfect. If I look here into my global, on how my global coordinates system is set up, I could also choose other coordinate systems, yeah, right here. But this is good for my purpose here. I press OK, and now I have my concentrated load at the correct place. One thing maybe I forgot to mention when I split up this member, or when I defined the additional node here, I have said I want to define my division 4.5 meters from the member start. But how do you know where or how your member is oriented? So how do you know which node is the start of your member and which node is the end of your member? And of course, you can somehow keep it in your mind how you defined the member. So in my case, I clicked this node first when I generated the line, and clicked this node second. So this gives me already the information that my line and also the member that is created on this line is oriented from this node to this node. But if I'm not sure sometimes, and sometimes the orientation is also changed by some operations, and you want to recheck, you can just quickly hover with your mouse cursor over the object, over the line or the member, and you see in your in a quick view a little arrow here, and this is indicating also the orientation of the member. Or you could right click and here show the local access systems of members, and that would also show you how the member is oriented in space with all its axes. All right, so I will now deactivate the local access systems again, and now we want to do our first simulation. Everything is set up, so we can now click on this button to calculate everything, or we can go through here, calculate all, or calculate current loading would also be sufficient for this case, or we could ask the program to show us the results. Then the program will remind you that we don't have any results to show and ask if we want to calculate, and we do so. And then we should be able to see the fourth tab of our navigator and see the results. First, we have shown the deformations here, and as you can see, the deformations are very, very large. So these are 99 meters vertical deflections, which of course makes no sense, but this is due to the fact that we just put a 1 in our stiffness matrix. So the bending stiffness of this exemplary beam is very, very low. Of course, this result would make no sense at all, but to review the internal forces and the support reactions, that's still good. So we can, besides the deformation in the global coordinate system or the local member coordinate system, we can assess the internal forces now. And if we check the shear forces on our member, that seems to be quite okay and correct. We also get a bending moment in around the strong axis with 18 kilonewton meters. That also looks okay and correct. And we can also activate the vision of our support reactions, and this looks also okay. It corresponds to the vertical forces. The sum is the same as the external force that we put in. So that looks fine so far. And yeah, of course, if we want to do some realistic design, we would be very alarmed by this huge deformations and would know that we have done something wrong, or we have applied the wrong theory to calculate it at least. Okay, so that would be the first example already done. These are the very basics, as example. Of course, you should never calculate something like this in RFEM. So you should be able to do it by hand. But the reason why I show this, or why it sometimes makes sense to also model such easy structure, is that of course for this system, you know already the answer. You can calculate it by hand and compare the results. And this is, of course, very important. With any software you use, you should first be confident that the results you are getting from the software are somehow realistic and are validated, and you can trust them. And for this purpose, it perfectly makes sense to also do such simple calculations to check if everything is set up the correct way. That's one principle of FEM analysis anyway. So from the simple structure to the more complex ones. All right, I don't know if there are any questions that we should treat at this stage. Maybe Richard can give me some short feedback, or if we should proceed with the second example.
Yeah, there are no open questions. You can continue.
All right. So we were very slow on this. We have to like increase the pace a little bit in order to get everything done. So I would now go to the second example, which is, let's see, in my PowerPoint. That was the first task we have already solved. The second example would be a two-span beam with altering load positions. So in this case, we shall model a two-span beam, now a steel section, HEB 300, with an S235 steel, and we have different load cases, so self-weight and an imposed load on the left side, and also an imposed load on the right side. And the goal is to determine the support forces and the like critical internal forces and deformation for the combination of loads that we apply here. By this, or in this example, we will go through the load cases and the combinations and the action categories and so on. All right, so let's go back to RFEM. We can then select everything, delete it by pressing the delete button, and start from scratch again. So we will now take a shorter route to define our member. So instead of defining nodes, then lines, then members, we can also already use this function new member directly to generate everything that we need to define a member. So I just click on the new member button. This time we choose the member type beam. And for this, we have to define, in order to get all the stiffnesses that we need for the analysis, we need to define a section and a material. And then the stiffnesses of this member can be calculated. So we shall create a HEB section. We can go to our library to create a new section. And this we can do by clicking on this book here, import section from library. Then we get a huge selection of section forms and profiles from the domain of steel design, or also some massive sections used for concrete design or timber design. But yeah, for us, this time we want to define an I section, and this can be found just in the upper left corner. We click on the standardized I section, and now we find a list of different profile series. we want to define an HEB. You can also filter here. I set the filter for European Union since we want to use the Eurocode for this webinar. I want to also select sections and material that are conform to these codes. So I could filter this here by region. And then I want to select an HEB 300 by going through this list. Then we can see on the right side, the section is yellow, so that means it has no material assigned. That is also indicated in the bottom here. So we can create the material that we want to assign to this section right here by clicking on this field. And this is the same logic as we defined the sections. We can also browse the material library to find the material that we want to use by clicking on this book button next to the name indication field, so to say. And then we have again filter to browse or to quickly find the material that we want to use. So we can pre-select a material type steel and a certain standard, in this case a European standard, and then we just take the S235JR. That's perfectly fine for our purpose. Click OK and OK again. Then we see that our section is now blue, which indicates that we have defined steel material for this section. So I think concrete would be gray and timber would be orange, so you can quickly differentiate between the materials that you assigned the sections to. So our section is now perfectly fine. We click OK. Yes, now we have our section. Click OK again. And now we are finally allowed to create our new member. So when I click OK now, we have defined our section and the material. When I click OK now, I can directly define my member. And I will do this by using the workspace now in this example. So I click into the origin and then generate the first beam, which should have a length of 5 meters, and a second beam for the second span, also 5 meters. So I click again on the first node, on the second node that I created, and then define the second beam. And as you can see on the left side here in the navigator tab, at the same time we defined the members, we have now also defined lines and nodes. And you can also see we have now, if we turn on the rendered view, we can see that we have a proper profile assigned here now. We can also switch to a wire model, but for this case, we will stick to the rendered visibility because I think it's nicer. And in this example, it's also quite easy to view to keep everything in keep track of the model. All right, so we have our members. Now we need to define our nodes again. So we can do it again via this tab right here. We can also use the table. Let's do this. So we go to our table. Under nodes, we double click on the options. Then also this context menu opens, or the edit node dialog opens, and we can assign a support. Support condition would be again fixed in X and in Z direction, but free to rotate. And then I use this option to assign the second and the third support. So this would be again roller in X direction, support type 4, and I can now also directly select both nodes to define the remaining supports at once. All right. Now this example is about combination, load case combination, and that's why here I want to activate my load case wizard again, so that makes it very easy to define load combinations that are compatible to Eurocode or other codes or design standards that you are designing with. So I go to base data, add-ons, and then select the combination wizard and classification and the load wizards again. That will enable me to use them in my modeling. And now you already might have seen that the color or the descriptor of my load case number 1 self-weight has now changed, and this is because I have now by default a standard assigned for the load combination. For me, this is predefined as the Eurocode 0, in 1990, and you can also choose national annexes. You can also here choose different codes depending on where you have to do your design. And I activate the combination wizard here again to get automatically created load combinations. And you can see here my load case number 1 is now directly assigned to an action category. So this or these action categories that you can assign to your load cases are predefined by the standard you have selected. So in my case, for the Eurocode 0, there are some predefined action categories that you can use. For example, permanent load, imposed loads, snow loads, wind loads, and so on. So the program knows how to combine the different load cases for your load combinations in the end. Please be aware. So this first load case is created by default. You should always, if you open a new model, there is predefined load case 1 as self-weight, and please take care or consider that by default the self-weight of the structure or of all the objects you are defining in your model is activated. So if you don't want to have the self-weight of, in this case, we have defined our members with a section, and of course this section has a weight, and if we don't want to have it considered in our calculation, we can deactivate the self-weight here. We have to uncheck it. And in many cases, if you have tasks in your studies to solve, you can neglect the self-weight of the structure, so you would need to uncheck this box. That's what we do right here. Instead, we want to define a member load in a few seconds, but before we do so, I want to create additional load cases. In the task, it was asked to also define a load case for imposed loads. I will just add another load case by clicking the generate or create new load case button here, and choose the action category imposed loads. It doesn't matter which category. For this example, I will stick to category A. And I can name this imposed load left to also know what this which load should be assigned to this load case. And I can also then just quickly copy this load case and rename it to right. So we also should create a load on the right side of our double span beam. So we have the 3 load cases set up. We can now check all the other tabs here in the load cases and combinations dialog. So in the actions tab, you can see that all the load cases you have defined, you have assigned them to a different action category, and all the defined action categories in your model are listed here. And you can change the way how the different load cases in this category or in this action category should be combined. So for example, for our imposed loads, we have two load cases that are of this kind of action, and we can choose under action type whether they can occur simultaneously or alternatively, or we can also define additional rules under differently. We can assign load cases in this action category to different groups and so on. But for this example, we will allow the actions to act simultaneously. This means they can also act alternatively, but they can act at the same time, but they can also act one for each other. So one for each. All right. Then under design situations, these are the load combination rules that are given by the standard. You probably know the difference between the ultimate limit state design situation and the serviceability limit state. And by default, these four design situations are created if you choose Eurocode 0 as the combination standard. You have probably seen these combination formulas or rules several times during your studies. You can click on the information button here to see how these rules look like how the partial safety factors are assigned to the different load groups and so on. And for this example, we will just consider the ULS and delete all the SLS design cases or design situations, sorry. All right, this is enough for our example here. Then in the action combinations tab, we see how these action groups are combined together and how the safety factors, what's the magnitude of the safety factors, of the partial safety factors for the action categories. Action category number 1 was our permanent load, and this is factored by 1.35, and our imposed loads by 1.5. So this is how those load cases or these actions are generally treated. And in the load combinations, we finally get all the combinations that we will run through our input to our simulation. So now from the load cases we defined and the combination rules that we have set, 4 different load combinations are created. For example, just the load case 1 plus load case 2, all 3 load cases, and load case 1 and 3. So every combination is considered here, but load case 1 is acting always because it's a permanent load. All right, so we have set up our load cases and combinations. We can click OK. Now we have to fill these load cases with, so we have to define loads for these load cases. This can be done quite easily. Now, in the last example, we defined a nodal load, but now we want to have uniform member load. For this, we use this generate new member load tool, for example, and we can assign it. So we are now in the first load case, self-weight, and we should create a uniform load for both spans of 2.5 kilonewton meters. So we assign the load to both members, member 1 and 2, and we enter a magnitude of 2.5 kilonewtons per meter, uniformly distributed in Z direction. So that's perfectly fine. We press OK, and we see our generated load. If I press enter now, we will just get back into the dialog, and we can define our second load for the second load case. We can just select load case 2 here, which has the imposed load on the left side, 5 kilonewtons. So we just pick our left member number 1. And we can also stay in this dialog, click apply and next to create the load, and then just be able to set up the next one. So finally, load case 3, imposed load on the right beam. We select the right beam. Also 5 kilonewtons per meter. Perfect. All right, we click OK. And now we can see if everything is correct. So we activate our loads. We show the loads. We can do that quickly via these buttons here in the toolbar. And then we can browse through our load cases. Load case 1, we have a uniform load on both members. Load case 2, just one on the left beam, and load case 3 on the right one. Perfect. So that seems good to me. And I think we are ready to solve this. So we press calculate all, and now it will calculate the load cases for themselves and also all load combinations. And we will now be able in the results to switch through the results of these load cases. For example, for the load case 1, self-weight, this is always unfactored. We get these results. We can check, for example, the bending moments here. That looks quite okay to me. I can, for the results analysis, go back to our wireframe model to better see the internal forces. So we have a hogging and sagging moments. The one above the middle support is the largest, as we would expect. Then we can go through our second and third load case, and also through our combinations. So combination number 1 would be just a factored result of the load case 1, but the others are combinations of all the load combinations, as you can see here. And now one task, or which is often you have a lot of different load cases, which results in which may result in thousands of load combinations in a real structure, and you are probably mostly interested in the critical internal forces and also the deflections, and these are can be shown or analyzed if we click on the results for the design situation. And now we get the envelope results that are shown here. So for every segment, we get the minimum result values and the maximum result values. For example, here we see the minimum and maximum hogging and sagging moments. So this is quite convenient. Also, the minimum and maximum support reactions are shown. And if we want to address the, for example, the vertical deflections, we can also directly see the envelope deflections here. We can also assess the results via the table. So one question was we should determine the governing load combination. So we can see the envelope here graphically, but we don't know in which combination, for example, do we get the maximum hogging moment here. So this minus 33.14 kilonewton meters, in which combination is this generated? And we can use the table, the results table, to check this, and we can go to results by member and then check for member number 1, and under these rows here, extremes, we can check all the extreme section forces. Now we have displacements here. We are interested in internal forces, sorry, so we have to switch the tab to internal forces, go to extremes, and now we can assess all the minimum and maximum values. So in this table, the section forces, for example, in this row, we get the extreme values for n, and this is for maximum value. Then in the second row, we get the minimum value for n. And this is everything is listed for all the internal forces here. And for example, for our bending moment around about the strong axis, we can clearly see that the maximum sagging moment is 23.94 kilonewton meter, which is corresponding also to the diagram here. And in the last row, we can directly see in which load combination this moment occurs. So the maximum sagging moment would occur in load combination 2, and the maximum sagging hogging moment, of minus 33 kilonewton meters would occur in load combination 3. Okay, for this example, this is probably quite obvious, but in more complicated structures with a lot of load combinations, this is a very convenient way to assess the critical load combinations for your structure and for the design. One thing I would also like to tell you, because this is often asked, so a lot of times students come back to us and say they have simulated a simple example and the results do not fit to a hand calculation. And this is because in our simulation, we by default consider the shear stiffness of our members. So in your hand calculation, or also in if you are using design handbooks or something like this, usually the shear stiffness of the member is not considered. So in order to neglect this in our program, you have the option to go to the section definition. So here we used our HEB 300, and in this edit section dialog, you can deactivate the shear stiffness of our member. And this leads to, it doesn't lead to larger deflections, because you would think, okay, now I have no stiffness. But if I deactivate the shear stiffness, this is means that I have infinite shear stiffness. So that that indicates that I don't have any shear deformation considered in my section. And we can just try this or check or compare the results. What happens when I sorry, we first have to check our results with shear deformation. So let's calculate it again, quite quick, and let's try to remember the maximum vertical deflections that we are getting here. So in this case, if we consider the shear stiffness, we get maximum vertical displacements of 1.2 millimeters. And now if we want to compare it to a hand calculation, for example, and we deactivate the shear stiffness, calculate it again. Let's see what happens. But we are now not considering any shear deformations, so our deformations decrease. So this is always something to keep in mind if you do a comparison. This is often the case why values are not exactly the same. All right, at that point, I don't know, I talked a lot now, and I would like to ask you now a short question regarding to the things I lastly said. So just to keep you awake, I start this short poll, and I hope you can quickly give me an answer to this question. It's just you have to think twice sometimes. But this is quite important. Okay, I see that a lot of attendees are asleep. Only 40% have already chosen. But anyway, I will now close the poll and show you the results. And yeah, most of you answered or picked the right option. The deformations tend to decrease, as we have seen now in the example. All right. So now let's move on to the third example. If there are no major questions that we need to clarify right now, I don't know, maybe Richard can give me a short feedback.
All fine, no questions open.
That's perfect. We don't have time anyway for this because we are short on time. I see when I'm looking at the clock. So let's move on to the third example. I will quickly show you the third task. By the way, you should also be able to download these PowerPoint slides. I don't know if you are able to download them through your dashboard or through your GoToWebinar panel. If not, you will receive these via email afterwards, probably next week. All right, now the third example is also a two-span beam, but in this case, a specific structure, a Gerber beam or a hinged beam. A Gerber beam is a statically determined system, and it's quite special because it has or it is designed to have the same hogging and the same sagging bending moment. And this is pretty useful for design of members because you can like optimize your utilization of the beam throughout the length. So if you have the same design strength in hogging and sagging moments, this is quite convenient to optimize your structure. And in order to create such Gerber beam, we just have to introduce a hinge, a member hinge, an additional one, and we have to find the right spot where we define this hinge in order to get the correct moment distribution. And we, at this point, don't want to reinvent the wheel, so I look into a civil engineering book and find this factor for my eccentricity of this hinge, so where I would need to place this. In Germany, we have a very famous book to look up such information, which would be the Schneider-Bautabellen. Here you find the reference, but probably where you live, you use other design books that have similar informations. And one special thing is we want to do the input parametrically, so we can later change the length of our span and have the member hinge always at the correct spot. So always at 0.1716 times the length of one span close to the middle support. All right, so we can leverage on what we have already modeled here. For the Gerber beam is also is only useful if we have uniform load. Otherwise, we cannot make sure that the hogging and sagging moment are the same by value or by absolute value. So we delete load case 2 and 3 and just consider the self weight, which is uniform throughout the whole member or the whole beam. And now we introduce a member hinge, and member hinges can only be generated at the end or at the start of a member. So we have to introduce a new division. So we have to divide the second member. To do this, I just right click on the member, and through our context menu, I use the function divide member. Since we want to set up a parametric solution anyway, I can this time use an intermediate node and just create it at a certain point, just to show you how this looks. I could now divide member number 2 in multiple slices of the same length. In this case, I want to just create one intermediate node. So when I do so, I have 2 members now with the same length. And then we, in the next step, have to set up our parametric model. So for this task, we use our use the possibility to define global parameters. We can address this via this little box here, or via edit global parameters. And there we get a table where we can create our own parameters. For example, we can create a parameter length, which describes, or let's just call it L to not get mixed up with the unit group, which describes, or which should in our case describe the length of one span. We have the unit group length, and then we can have or assign a unit to it, which is relates to a distance. And then we enter, we had a default value now for our fixed model, we have 5 meters. So we, in the first place, just enter this and adopt this value. So we put input L is equal to 5 meters in the first place. Then we need a second parameter for the eccentricity of our member hinge. And this would be, we just call it E as in the task description. This is not a length, it's a unitless factor. So we just choose the unit group factors and assign a value of 0.1716, as we have looked this up in our design handbook. Press enter. All right, now we have our parameters set up, and we can now use these parameters to define the location of our nodes. So everything here is connected with each other. So if I change, for example, I can now in hindsight change the position of this node, for example, and it would sync up with all the other objects that I have defined in my model, because the lines and the members and so on, they are related to this node, and they are modified accordingly if I change the position of this node. And I can set the position of the node by also by double clicking it and then putting in new coordinates here. And instead of inputting fixed numbers, I can also go on this right arrow button here on the right side of this input box and input a formula. And then I can use, in this formula, I can use numeric values, or I could now also use my parameters that I have just defined. So if I put in L here, it also gives me a short preview of which parameters I could use that start with L. I could also assess a lot of other parameters that are related to my defined objects, but let's stick to the global parameters that we have defined manually in this case. And if I select this one, I also I already get in my preview the result of this formula, just L, is 5 meters. I press the OK button, and now my X coordinate is still at 5 meters, but now it is linked to a formula, and it is not fixed anymore, but it depends on the value of L. And this is indicated by this small yellow object here in the left, the triangle here in the left upper corner. So I click OK now. I have parameterized the X position of this node now, and I want to do the same for the other nodes, the other 2 nodes that are on the right side of this one. So the last node here is at 10 meters. So that would be, I added this formula that would be at the position of 2 times L is equal to 10. We can see that in the preview already. Click OK to take it over. And now I see, okay, it's now an interactive value. And last but not least, we have to change the position of the newly generated node 4, that where we want to introduce our member hinge. So we do the same procedure, but now we have to think a bit more when we define our formula. So this node should be at the position 1 plus E. This is our eccentricity times L. And that should be okay. We could also write L plus E times L. That would be the same. This is a bit more elegant. Press OK. And now we can already see that this node was adjusted. So it was automatically moved to the left. We had formerly just defined it somewhere here on that beam, but now it's on the right position. So yeah, we also see here in the table that these three values are now somehow connected to a formula. And the last thing we have to do is to introduce a member hinge. And we, as I said in the beginning, we can introduce it at the member start or at the member end. In this case, I will do it at the start of this member here. So I double click on the member. Then I have the option to activate a hinge. If I do so, another slide or another page appears where I can make adjustments. And here I can assign a member hinge to the start of the member. And I will do so. I have not defined any hinge type, so I have to define a new one. And this is the same logic as for the nodal supports. So I have my degrees of freedoms and I can account for them or not. But in this case, I have to check the degrees of freedom that I want to release. So if I want to have a moment hinge here in this at that point, I have to release the rotational degree of freedom like it is already assigned by default. So that would be a hinge definition that would suit my purpose. I click OK. At the member end, I don't want to have any member hinge, so this is okay. And if I click OK, I see that now I have a white dot here just next to this node, and that indicates that I have a member hinge at the start of this member. So I think now we have, we are finished with everything we need for the calculation. I will just quickly add some dimensions to it so we can follow this as we change maybe the parameters later. All right. And now we just quickly calculate this load case and see if we get the results that we wanted. So we wanted to have the same hogging and sagging moment, looking at just the pure value. I deactivate the visibility of the loads and change to wireframe rendering, and we can see that the result is pretty much that what we wanted. So the moments are regardless of the sign, so neglecting the sign, they are almost the same. There are some rounding errors probably. Also, we have input the eccentricity just with 4 digits after the comma, so that can be the reason why there are some slight deviations, but overall it's I would say an acceptable accuracy and it looks fine. And the nice thing is now we have defined this in a parameterized fashion. So if we want to perform this simulation on a Gerber beam that has a span of 3 meters, a length of 3 meters in each span, we can just quickly go to our global parameters and, for example, adjust the length to 8 meters. Let's do so and see what it does. It will now, of course, delete all the results because the model geometry changed. Yeah, and we can now see that not only the length of the span has changed, but also the distance of this hinge, but relatively they are at the same spot. So if we do the calculation, the simulation now again, we should still, of course, we should have different bending moments resulting from this, but they should be equal regarding if we neglect the sign of it, and they are. So this is a nice and easy way how to introduce parameters to your model and yeah, avoid repetitive work, especially if you are at the beginning of your design process. Sometimes it's not very clear how you set up a certain structure. So this is a nice way to do so. All right, then let's see, are there any questions here?
No.
Maybe I can ask you something now that we have done a bit of modeling here. I would like to ask a basic question regarding the user interface and how to use it and how to model all that, the nodes and the members and so on. So my question is, do you remember or do you know where I can create objects such as nodes, lines, and so on that we have used now for the last examples? So in this case, you have the option to select multiple answers. So it would be nice if you give me your, or tell me what you understood from my explanations. I see that most people are favoring the toolbar, and this is probably because I used it the most. All right, then I would close the poll and share the results with you. And yeah, it's quite mixed. As I said, the toolbar is winning, but the right answer would be everything. So you can define all of these objects in all of these parts of the program. But as I said in the beginning, it depends a bit on what you prefer, what's your preferred style of modeling, and also how you can leverage a certain function in your system. So sometimes I would prefer the table input over the toolbar, or sometimes I would use the navigator input. But that is something that comes along with the usage of the program. All right, thanks for participating anyway. So let's check our schedule. What do we have next on our list? There is another example, but this one, yeah, would be, I would leave it as a homework, so to say. You could now take everything you have learned. Here we define some loads, members, and so on, and you could try to model this clamped beam with a cantilever with some funky or more special load definitions on your own. Maybe I can show you just the basic definitions on how you define such loads. So for example, this in our case here, we have defined a uniform member load, but you could also define trapezoidal loads, and the triangular loads that you have just seen in the task are nothing else than a specific sort of trapezoidal load. And you can enter, but this is mostly self-explanatory. So if you check the helping figures on the right side, you quickly understand that you have to put in the load at the start of this load definition, a load magnitude at the end of this load definition, and you can also put in the distance where this load should start and end. And for this one, I have just a short quick tip for you. You can switch between inputting absolute length in meters, or you by pressing this percentage sign here, you can change to relative distance. And we could, for example, now say create a triangular load starting at 20% of the length and going to 80%, and that would be the outcome. So we have a short gap until we start with the loading. And then another load type that is that you have to define in this example would be imposed nodal deformation, and you can find those here. It's another load type. And here in this context, it is very important to mention that you can only input imposed deformations where you have defined nodal support. So just for the degrees of freedoms, you have defined a nodal support. You can also define an imposed deformation. So for example, for this node right here, I could define an imposed displacement in Z direction, since this is a degree of freedom that I have fixed by just putting in a deformation. You can also get a nice preview in this dynamic window over here, but I couldn't assign a rotation because I have not fixed this rotation in my nodal support definition. So if I would click now, okay, it would be saying that this nodal support is not held in the direction of deformation, and it has a problem with this imposed rotation. So if I delete it, that should work. So deformation in Z direction is allowed because I have fixed this this degree of freedom. And then maybe the last hint would be if you define a nodal load, you can define it via. So what we have done here was we define, until now we defined a nodal load in a certain direction, but we can also define the load by components. So we could, to get a load that's acting under a certain angle, we could put in a value for fx and fz and make sure that the resultant has the desired magnitude and also the direction is correct. But we can also put in a load and then apply a specific direction by clicking this option here. And then we get another tab where we can put in a rotation and a rotation axis. In this case, there's only one axis where we can rotate our load because we are modeling in 2D. So let's say we want to define a load on this node, and we can easily change the direction by putting in a value here. It should update when I need to somehow change something, but then it also updates the preview here, and you can see it's just rotating, and I don't have to do any calculations with Pythagoras or sinus, cosine, whatever. This is a very convenient way to define a load under a certain angle. All right. With this being said, I would like to go on with the last example before we make a small break. And that would be this two-hinged frame with the tie rod. I would say I would you should focus maybe on what I'm doing and stop modeling alone, because I want to increase the pace a bit. And a lot of the options that we have performed now are repetitive. So yeah, just look what I'm doing and listen to my explanations. That should be perfectly fine. So to define this two-hinged frame, I first delete everything again, and then I first define the frame. So the frame consists of two beams. We leave it HEB 300. The section is fine, so we can leverage on the settings we have already made. I have the beam has a height of 5 meters, and then we define the first girder, roof girder, that should be at x equal to 5 and should be 3 meters above the column. So that would be the right location here. I use the grid to snap my object, so to define the members. This is very nice to use the grid here. You can also, if you have some strange distances and you would like to alter the distances between these dots, you can always change this in your work plane and grid options. So I could, for example, if I had a smaller model and I would need to catch every 10 centimeters or so, I could decrease the size of the spacing, for example, here, to set it up for my modeling. Okay, and this time I also want to show you another function that will make your life easier. When modeling something that is symmetric, you can use the mirror function that you can, for example, access over here. So I select my objects. Maybe I also, before I do that, I also define my nodal support, so I can mirror this as well. So this should be a hinged support. And now I select all my objects and I want to mirror it. So I use this function mirror selected objects. Then I don't want to just mirror it. I want to also copy it. I want to have a copy of the objects at the other side. And I can define the mirroring operation by a mirroring plane through a point and a parallel plane. So I want to mirror it about the YZ plane. And then I have to put in a point that should lie on this plane. And I could, for example, take this upper node 3 here. And there are some useful options. Sometimes it's also useful to copy not only the selected objects, but also loads or imperfections. But in this case, this is sufficient. And if I press OK, I have the other side of the frame generated very conveniently. So now I only need my tie rod. So I need another member that I want to define. And in this case, I don't want to use the member type beam, but I want to use a member type that only takes normal forces. So a tie rod, I want to define it as a very compact but small section. I want to use a round profile that cannot take a huge amount of bending, but is only used for taking tension. So in this case, I could, for example, take a truss element that can, and there are two different truss elements. One truss element, or the green one up here, if we click on it, it is like a beam element, but with member hinges, rotational hinges at the end. So it can still transfer vertical forces. So for example, if I apply a load on this truss member in the middle of the truss member or so, or the just the self weight of the truss can generate bending moments in the truss, and then I have the element truss only n, and this one would not consider the bending moment or shear forces whatsoever, and just transfer normal forces. And then I have a very specific elements like a tension element or a compression element, and these ones I can use, for example, when I want to define a tension rod. You will see that the section that I define for this is very suspective to buckling, so it cannot take a lot of compressive force, and that's why I want to define it as a tension member. So this member will only be allowed to take tensile normal forces. Yeah, as I said, I want to define another section for this tie rod. A typical one would be, for example, a round profile, let's say with a diameter of 30 millimeters, so like a cable, so to say. And we will use this to keep the frame together, or to increase the stiffness of the frame significantly. All right. Now that we have defined this, we need the loads. So we have 3 different load cases that we want to consider. The first one is snow, so I will also show you how to quickly generate those load cases directly in the correct action category. First load case, snow. Second load case will be wind. Action category is set up accordingly. And the third one will be temperature elevation in the frame. So this is also a known category, temperature non-fire. Okay. And yeah, we are not, in this case, we are not interested in the design situation, so we delete this. We just want to look at the different load cases. Okay, so let's set up the loads. Snow load, this is also often asked, like if you design in timber design also a roof, and you the task is to define the correct magnitude of snow and wind and self-weight, and how you have to orientate and project them. This is always a task that is like common in studies. So if I want to define snow for the beam girder, for the roof girders, I first select them, and then I define a snow load of 1 kilonewton per meter. And now I have to pay attention. I want to define it in the global z-axis, but in this case I don't want to project it on the true length of the beam as I would do for self-weight, for example, but I want to project, or I want to assign it on the projected length on the bottom, like so, like indicated here in this preview here. I press OK, and the snow load should be generated. Next, I generate my wind load, and this is also a typical case. I again define a member load. Now I want to do it in a very simplified manner and just assume that we have just wind pressure on one side of our small structure here, no suction and no different like wind load zones. So I just pick these 2 members here on the left side and assign wind pressure of 1 kilonewton. And when I talk about pressure, we should now also set the direction of the load very carefully. We don't want to use the global system for this, so wind pressure or pressure in general always acts perpendicular to the beam axis or to the object axis. So we want to use our local beam axis, a coordinate system, and this is also one thing to mention. The local coordinate system is by convention described by small letters x, y, z, while the global coordinate system is like described by the big letters, capital letter x, y, z. So this is very common for a very common convention for analysis software, but also hand calculations, I think. Yeah, and now we want to assign the pressure perpendicular to the beam axis. So that would be the correct, Z would be already the correct orientation for it. If we are not sure, we can also click on the preview and we can see how our beam is rotated, but that looks perfectly fine to me. So I click OK and the wind load is generated. In the last load case, number 3, we want to create a temperature load case. So in this case, I assign it to all frame members. I can also, as I just did, pre-select the members and then click on define member load. So I don't have to assign them afterwards. And we, besides the force load type, we have several other load categories, and for our case we want to apply a temperature and then we have the option to input 2 load parameters. On the right side we have a little description on what the parameters describe. So TC, I think that should be in this case TT. It's not okay. That doesn't seem to be. I think this is for German language, and it is not counted here in the parameters overview. So that's wrong. But I think TT should be the average temperature increase of the section, and TB should be the difference between the lower side and the upper side of the member. So in this case, we want to apply an average heating of 35 Kelvin or degrees. So we can just enter 35 degrees to TT, and we can check if this is correct. Should be correct. Press OK, and now we have defined our TT value. All right, then let's calculate all of our load cases. We can use the calculate all option. And review the results. So I think I applied the temperature wrong. Sorry for this. I probably have the wrong load definition. Let me check. Temperature member load. Sorry, I entered the wrong load type. So I wanted to use the temperature change, and now the parameters also fit the description. I want average heating or temperature increase of 35 degrees. I was just wondering why the results are off my expectations, so I will quickly adopt this and calculate it again. Now we should see that the temperature rise, like it tends to the frame wants to go wants to expand, and if we look at the internal forces, the normal forces, we can see what the tie rod is doing here. So it's taking a rather large normal force, a tensile force, to hold the frame together, to constrain it. Then in our snow load case, it's yeah, a bit the same. So we have a vertical load on the roof, and the frame also tends to go to the sides, to move to the sides, and the tension rod helps to minimize the horizontal deflection at the column ends here and tie it all together. And then let's check the wind load case. Here we have a special case because, as you can see, this tension rod is marked in gray, and this is because in the wind load case, our tension rod is not active, because here it would be loaded in compression. So if we would define it as a truss member, it would have compressive action, and we define it as a tension member. So as soon as we get a negative internal force in here, it's deactivated for further calculation. So this also requires an iterative solution. So in the first iteration, this tension rod would be activated, and then the program sees, okay, we have a negative internal force, it's under compression, but we defined a tension member only, so it's deactivated in the next step, and the solution is done again without this member. So this is indicated by the gray color of this member here. All right. So that would be our last example before we go into a short break, I would say. Are there any essential questions that we should answer at that point, or?
No questions open.
Okay. All right. That's good to hear. So I would say we make a small break. Let's meet again maybe in 10 minutes, I would say. So 6:10, so everybody has the option to grab a drink or a coffee or a short snack. And then we meet here at this place again at 6:10. Yeah, European time. So in roughly 8 minutes. All right, thanks for your attention so far, and see you soon. All right, I hope you had a good rest. I'm back now. I would say we try to continue. And maybe until everybody is here, I can just take this chance to ask you another question, and then at the same time check if everybody is there and ready to go ahead. I introduced myself in the beginning, but I don't know anything about you, and I would like to ask you also, before we go to the advanced topics, how far are you in your studies? So if you could answer this, also if you are no student or do something else and are just interested, this is also fine. But that would be interesting for me just to get an overview how experienced you are in civil engineering. Okay, fine, interesting. Then I close the poll and show you the results. So none of you is in the first semesters of his bachelor studies. Most of you are quite advanced, so that's nice. Also for the following topics with theory second order and the buckling analysis that we will treat at the end of this online training. All right, so but before we come to this, let's do another modeling example. So another example where I will focus on modeling options and how you can do investigations and simulations quite quickly and conveniently with RFEM 6. And for this task, I have an ideal trust structure that we want to model. You can also, in this case, just relax and listen to and see how I do it and how I define the structure. I think this is more convenient now, also looking at the time. All right. So we have, sorry, just for the problem that we are having here, an ideal trust structure. So that means
Jonas, you must close the...
Okay, I have, yeah. I again forgot to hide the results. All right. So now you should see my PowerPoint presentation again and the task that is waiting for us. So it is an ideal trust structure, as I mentioned already. That means we have only trust members that transfer basically normal forces. We have perfectly hinged connections between the members. We have no imperfections between or in the members. We have no eccentricities in the connections. So we have no additional bending moments because of this. And we only have loads defined in the nodes of our ideal trust structure. So these are the basic assumptions that go along with this term, ideal trust structure. So that results in only normal forces or actual forces in the trusses. All right, let's start then with our simulation work. We again delete the last bit of structure that we have defined. Oh, there's this one we can also delete the load cases that we won't need here. Okay, and then we start with the modeling. So in this case, what's a bit special is that the first beam that leads from the lower to the bottom chord is defined under a certain angle. And for that purpose, to define such beam, it's very convenient to use the single general member definition, because here we are allowed to define our member by length and direction. So we have a member length that is given with 3 meters, and we can also additionally to the length, we can put in an angle under which we want to define this beam. And now you can see I have my member in the preview attached to my cursor, and I can put it down everywhere I want. So again, I will start in the origin. It's very convenient for me. And then in the next step, I will again use the mirror function to make a copy of this diagonal. The point where I want to define the plane should be this one. Create copy, yes. And then I close the triangle by defining the third beam down here. So now I have one triangle, and this truss structure should have 3 of them. So now I want to show you how you can conveniently copy such substructures. So if you just select everything and then press the Control key, you can copy via drag and drop, and you can also snap through to the existing structure to make this the common node of both selections. So now I have just duplicated my triangle. I can also do this, of course, with the whole group of objects, but this would be one too much, one span, so I delete this one. Now I just have to add the upper chord. We stick just for convenience with the HEB section, so we don't have to redefine this one. And then the only thing missing with regards to our members would be the posts, and we define one in this to split up this triangle. So the default snapping points for object generation or selection are the ends of a line or a member, and also the middle points. So this is very convenient in our case here. Now we can just generate this beam here by snapping to this point, and now we could again copy this post by drag and drop, or in this case I would prefer this this functionality, move and copy selected objects. So I create a copy, and now I can create multiple copies in one step. So I count how many posts do I need? 1, 2, 3, 4. I need 4 additional posts. And okay, I don't really know the distance between this point and this point, so I can also define the displacement vector graphically. So would be from this point to here. And the distance between the posts is, the spacing is continuous, so this should give us the desired result. And now if I click OK, I have just defined all the posts at once. So this is very nice. Also, if you define structures that are built of frames that are repetitive, or structures like truss structures where you have always same sub or super elements that you just need to copy to get your complete structure, this is very convenient. All right, then we have to change the beam type. So I accidentally defined them as member type beam, but we said we want only trusses, so trusses with only that can only transfer normal forces. So we would need to change the member type to truss only N. By the way, if you are not sure what these member types mean and you can't figure it out by the preview here, it's always a good thing to open the help. We have an open manual attached to RFEM and Erstab, and the cool thing is if I press this little tiny button here in the lower left corner, it opens my browser to access this online manual, and it opens the correct section of it right away. So if I click this dialog from the or this icon from the members dialog, I directly get the help for members, and I can quickly browse, for example, here through all the member types and what they mean and what are the assumptions of these member types. So this is very convenient, and you can find this little help box in a lot of places in the program, so you can quickly get to the right point in our help documents. So, okay, I change the type now. I see in the preview that worked. So then I need to define supports. I just do it by adding a support here, hinged, and I think this one would be, we could define it just in a roller in X direction, should be fine. And we had on the upper chord, we had some concentrated loads in the nodes. So we had, I think in these 2 nodes, a load of 10 kilonewtons, yes, and in the third one, 20. So let's define this, 10 kilonewton in these nodes, and in the third one it's double, so 20. Okay. I think this should be it. We have defined this as load case 1 snow. We can of course change that, but I think for our purpose here, we just want to see the results of this one load case and check like which are null members under these loading conditions, and which members are compressive and tensile members. So for this, it doesn't matter which load case and how this is and which action category I have assigned to it. So I will just calculate this load case and go to my wireframe view. And now I can quickly see which members aren't loaded at all, so which members are null members actually. This is also a topic that is often asked in student assignments or so. So these posts do not do anything. They could just be striked out. And I also get a very good overview about which truss members are compressive ones and which are tensile members. So the negative forces are indicated by the blue color, and the members that are red or have normal forces displayed in red are the tensile members. So compression in the upper chord, tension in the lower chord seems fine, and the diagonals seem also reasonable. All right, that would be it for this task. And now in the next one, I quickly want to show you how you can very conveniently define such truss structures that are repetitive and very generic through our block systems. So in our program, I delete this. In our program, you have the option to open the block center. And these blocks are predefined structures that can be very tiny, so just one girder, but they can also be quite complex. You can assess real buildings and large structures here in this block library. So this is very cool. So and the good thing is these blocks are not static models that you can open and then simulate, but you can manipulate them and modify them to your needs. So if we, for example, go to trusses, you see there are a lot of trusses already defined, and we will just pick the simplest one here, FT001A. Double click it to open this block. Okay, it says, okay, this block is model type 3D. So do you want to change? Yes. Okay, we go to 3D model now. And you see that under structure, you can now change a lot of parameters of this truss. So we can, for example, change the number of bays. Let's do 4, for example. We can change the length of the base to 3 meters. We can change the height. We can change the materials and sections for the different structural elements. For example, we can say the diagonals. We want to define a slightly smaller section. In this context, I would like to show you a nice work or a quicker solution on how to find the section you want. So if you already know you have a standardized section and it is a common description to it, for example, I want to have now an IPE 160 or something, then I can just enter here in the name field my the description of my section, and I find through a quick search all the options that or all the sections that have this in their name. So, and I can very quickly select an IPE 160. Oh, now it changed everything. Okay, I didn't want to change this, but I wanted to make it optional. Let's change this back to an HEB 300. The problem is sometimes, okay, it now also finds an HEBT 300. Okay, that contains all the things I entered here in HEB 300, but it's not an exclusive search. So if I want to search exclusively for HEB 300, I have to put quotes on it, and then I only get the options for the HEB section. I can reselect it here. And now I want my diagonals to be section 3, section type 3. This can also be section type 3. I can define or redefine my supports, but that seems fine. And then I can click OK to put this in my model. And you see these nodes, lines, and members are in have a weird color. So far they were always black, but in this case they are pink. So this indicates that these members are related to another super element or this block, and I cannot or should not directly or should not change these nodes or lines separately, but instead they are still attached to this block object, and I can still change the definition of this truss by manipulating the values in our block. So also after defining it, I can still change it via this this manipulation tab here structure. And if I want to loosen the connection between the block and all its objects, I can right click and convert into a normal geometry. And now I see all my objects have the black color again, so they are independent now, and I can play around with them freely and independently of all the other values and restrictions. But these blocks are a very nice way to quickly generate structures, or to even whole buildings can be plugged together by using these blocks. And what's behind it is a script, a JavaScript. So this gives you an outlook on how you also can use RFEM, because RFEM or RStab allows you to generate such scripts where you can define, for example, your own blocks with all the input parameters that you desire, or you can use these functions to generate models aside from these block functions. We have a scripting console which you can just use to generate nodes, members, lines, and any other objects via commands. And you can find these by inputting the commands, and it has an autofill function, or clicking the information here, you can find all the objects and the syntax on how you can relate to them. So this is very cool and provides you with plenty possibilities for further use. So that I just wanted to scratch and to show you that something like this is also possible. And now that we have done this, I would like to go to the next level with you and take a look into the theory and how you can change it for your for your calculations, for your simulations. If there are any questions, maybe Richard, you can give me a short feedback. I can also answer them and pause for a bit. Otherwise, I would talk to you a bit about how to consider nonlinear deformations. So far in our examples, we have always solved our problems assuming a linear deformation theory. So the equilibrium between internal and external forces was derived based on the undeformed structure. But as you probably know, this is not always permitted. So if you have slender or flexible systems, you want to at least investigate the influence of nonlinear deformations or of the undeformed structure of the deformed structure on the internal forces and reactions. And in order to account for this in your RFEM simulation, this is quite easy, and we want to introduce, or I would like to introduce this step by step again in a small example. So we will take a fixed column and apply a head load and see how the results change if we switch from first order theory to second order theory and account for the nonlinear deformation. So let's do just this. We delete the truss again, generate the column. It's 10 meters. I don't know what section was this. HEV 300 is fine. Then we fix the base of the column and make a solid render because we want to know how the member is orientated here. The support seems to be a bit small now. I can quickly adjust the size of it by right-clicking on it and then adjusting the support size. It's just viewing preference. And then I will apply a nodal load at the end of the column, and I want to apply a vertical load of 100 kilonewtons and also at the same time 10 kilonewton horizontal load in X direction. So I press OK, need to select the node, and here we go. So now, first of all, in the first step, we want to calculate it without considering large deformations or P delta effects, or how you have learned this theory to name. So in order to make the correct setting, you can go to a load case, and here you find the category static analysis settings that you can assign to a load case, but also load combinations. And by default, for load cases are calculated assuming geometrical linearity. So there are 3 different static analysis settings that are predefined if you open a new model. One for theory first order, that would be geometrical linear. The second order theory and large deformations. The difference between second order theory and third order theory is that with the large deformations or third order theory, you can also account for large rotations. So if you have a very large displacement and rotations, I would definitely recommend to go for the large deformations theory, or at least check the influence of it if you are not sure. But we want to go with the geometrically linear analysis for the first in the first part. You can also adjust some additional settings or generate additional static analysis settings in this dialog by manipulating or generating a new one here with these buttons, or you could access this as well under static analysis settings. Here you have listed all the settings that are defined in your model. But yeah, let's do the calculation first using first order theory. Show results. What do we get? I think this is, this shouldn't be any surprise for you. So let's scale the viewing up a bit. Okay, so first of all, we get a normal force of 100 kilonewtons compression. Okay, that's totally fine. We applied 100 kilonewtons. We have a constant shear force in that direction of the profile. That's also as we would expect, and a linearly increasing bending moment with a 100 kilonewton meter at the clamped end. So 10 kilonewton times 10 meters. So that is what you would expect from your hand calculation. We would need to also activate the moment nodal supports to see them, so don't be surprised, but I will probably switch them up for better visibility. Okay, now let's see, and one thing we can also check out, which is interesting, would be the deformations in x direction, or the global deformation in x direction. So the end of the beam deflects about 63 millimeters in x direction under this 10 kilonewton horizontal load. And let's see how the results change when we now apply the second order theory. So we, for that purpose, or for better to check the difference between both theories, we just copy the selected load case with all the loadings defined in it, and we change the static analysis setting of our load case 2 to second order theory and calculate this as well. And what we already see, our global deformation in x direction has increased slightly, about 10%. So from 62.5 millimeters, we have now 68.7 millimeters. And now let's go through the normal forces. Okay, they look quite similar. So we have not perfectly 100 kilonewton here, but almost. Then we see, okay, our vertical or shear load here has increased, and our bending moment at the fixed end is now 107 kilonewton meters almost, where we had 100 before. So our bending moment at the fixed end has now increased by almost 7%. And this can be explained by the eccentricity that we have. So we have, because of this horizontal load, we have a displacement of the member of the column head by 68.7 millimeters. And this eccentricity now creates an additional bending moment because these 100 kilonewtons now have a distance in x direction to the clamped end of 68.7 millimeters. So we get an additional bending moment of 6.87 millimeters. So 100 kilonewton times 0.0 almost 7 meters, we get an additional bending moment of almost 7 kilonewton meters. And this is what we see here. So it is very in this case, okay, like 7% is not too much. We could probably neglect the influence of a second order theory in this case, but you have to, of course, take into account that this increase of the bending moment of the internal forces is not proportional anymore to the loading you put in. So if I double the load, then we will see, let's check out how the bending moment at the fixed end increases. We calculate it again with 200 kilonewtons and 20 kilonewtons at the column head. And we see that now our bending moment at the column end is 230 kilonewton meters, or almost. So we have an increase of almost 15% now. That's more than double than we had when we applied 100 kilonewtons and 10 kilonewtons horizontal load. And of course, this can also lead to an unstable structure even. So if we further increase the loading to, let's say, 500 kilonewtons and 50 kilonewtons horizontal load, the solver of RFEM will not be able to find a convergent solution. So it will not find any equilibrium between the external forces and the internal forces, because the deflections are too high and the structure is unstable and is not able to withstand the external load of this magnitude. So you can use the second order theory in RFEM to consider or to take into account stability issues, like in this case. So if you wonder why a structure gets unstable under second order theory, that could be related to a stability phenomenon of your structure. And another way to address stability problems or phenomena and to better understand what's happening is to do a linear bifurcation analysis, which can also be done in RFEM. And that we want to do in the last step of our online training. So I will slightly modify the structure. I will just delete the second load case and will delete the horizontal force, and you will see that this leads us to a quite an iconic structure, or let's say element. This is a structure that has been investigated for stability for a long time. So I think Leonhard Euler already in the 18th century provided a solution to address stability of such fixed end beams or fixed columns under pure compressional load analytically. But this means we can also check the results that we obtain with RFEM very easily and check if the results hold against the analytic solution. So yeah, this is also known as Euler case number 1. And let's see what settings we have to do an stability investigation with our RFEM 6. So to do that, we need to activate an add-on. I showed you that very briefly in the beginning. So we have under base data, we have the option to activate several add-ons if you have access to them. And for this case, we would need the structure stability add-on. I will go ahead, check the box. And now I have the option or the possibility to add a structure stability calculation to my load case that I want to calculate or to assess. I can also do that for load combinations. I just have to activate this option, calculate critical load, with the structure stability add-on, and yeah, then just as we did with the static analysis settings, we have structure stability analysis settings that I have to set here. I can change them again by clicking one of those buttons. I can see these are the two analysis settings that are usually defined. So the first one is perfectly fine for us. We have 4 eigenvalues that will be calculated here. So that will be very much sufficient for us. So let's calculate the load case now with the activated structure stability analysis. So we see we have now 2 analyses that are performed. One is called SA1 and one ST1 for structure stability. And we also have in the results navigator now 2 options to choose from to assess results: the static analysis and also the stability analysis. So what was done with this within the stability analysis, or what is the concept behind it? For the given structure and the given load, the eigenvalues problem of this structure is solved, and as a result we get eigenvalues that are here given as critical load factors, and these critical load factors finally tell you or give you the information of how much you can increase the given load, or you have to decrease your given load to remain stable with your structure. So in this case, I have the first eigenvalue was found at 4.433, and this means I could multiply my given external load by this factor, and then my column, this fixed column, would get unstable under a second order theory calculation. So this is very important information for us as engineers. The second result are the eigenvectors, and these are the nodal deformations of our that are calculated for our structure. So we can also check the deformations or mode shapes that go along with our eigen values. So for example, for the first eigen mode, we would get a critical load factor and this eigen shape, and this indicates a buckling of our fixed column around its weak axis, as we would expect. The second eigen mode seems to be buckling around the strong axis. It has a much higher critical load factor if we compare it, and that's what we would expect as well. The third and the fourth eigen mode are some higher modes that are probably not critical for this structure. So usually only the lowest critical load factor is interesting for us. Besides, we also get this magnification factor, and this is just a rough estimate on how second order theory would influence our internal forces. So there are some, for example, according to Eurocode 3, so the steel design code in Europe, it's sometimes allowed to consider the effect of second order theory by applying this magnification factor to the first order internal forces. So that's expressed by this magnification factor, but this often leads to confusion between both factors that are calculated here. The most interesting one would be, of course, the critical load factor for us. Okay, another nice result we get from this stability analysis is we can look to the results by members, and here we have a tab effective length and critical loads by member. Or let's see the ones by mode shape. And now we can see for our first mode shape, we get an effective length factor of 2. And this is exactly what we would also get from the analytical Euler solution. So for Euler case 1, we know that we have to apply a factor of 2 to our structural length to get an effective or equivalent buckling length. And this can be calculated also with this add-on. The same goes for eigenmode 2. Here we get also an effective length factor of 2. We only can take or we always have to relate the effective length that we calculate here to the eigenmode. So for buckling around the strong axis, we would of course need to consider this effective length of this eigenmode and not the effective length given by eigenmode number 1. Yeah, so this is a very nice tool to also get effective length and critical loads for structures and systems that are not as easy as this one and where we don't have an analytical solution. For example, for frames with different length of the columns, or columns that don't have a prismatic cross section, but it changes along the length, or where we have a non-uniform loading or whatever. There are a lot of scenarios where we will not or cannot work with the analytical solutions, and therefore this is very nice. The last example I want to go through with you would be one of those structures. So I would like to model or to change this single column to a fixed frame and see how the results alter when we copy the column and connect it by a beam. So let's see how the results look for such a case. So we have to shorten the column. We can just do this by drag and drop this node. I think the columns of the frame should be 6 meters long. So now I dragged it down 4 meters. Then I copy this, including the load. Create a copy, only one. The frame has a bay length of 10 meters. And I also want to include the loading when I copy this. And then I connect the two columns by a girder, like so. All right. Everything else can probably remain like it is. I hit the calculation button, and let's see how the eigen shapes look for this case. Let's browse through the stability analysis results, and we see that we now have the first two eigenmodes that are out of plane stability cases. So in the first eigenmode, the whole frame would swing out of the frame plane. So in this case, our frame does not help with the stability. But if we look into the in-plane stability modes here, we see that the critical load has increased drastically. So by adding this girder, we add additional rotational stiffness to the column end, and we can pretty much increase the resistance of this frame against buckling in plane. So, but in real structures, you would probably not have such a separated or isolated frame, but this frame would somehow be restrained in y direction or braced in a structure. You could have like another frame here and another frame, and somewhere it should be braced, or it should at least have some compressive links between those frames. So it usually cannot move out of plane like it does here. And if we want to prevent such eigenshapes or such out of plane sway movement, we could define a nodal support in y direction, and by doing so simulate the horizontal supports at the corners of this frame. And if we do the same calculation again now, we will see that we won't have this frame sway motion anymore, but the critical eigenform will be in plane now. So of course, if you do such simulations or analysis, you have to make sure that your supporting conditions and also the connection of the members and so on, you have set them up realistically. Of course, we in this example have rigid connections between the girder and the column, but in reality you would probably have a certain stiffness between them that you could take into account and so on. Yeah, but I just wanted to show you that this is a powerful tool that you can use to also do stability analysis for more complex structures, and showed you some easy examples to get used to it. And I would invite you to just play around with it, recalculate the Euler cases, and then move on to more complex cases with it. All right, and with this example, I would like to close today's online training. Unfortunately, there's not much room for questions anymore. We have like 1 minute left. If you have any additional questions that have not been answered now in the webinar, I would also invite you to send your, oh sorry, now I mess up everything, to send your questions via mail to our support, to info@dlubal.com, and we were very happy to help you with it. Also, make sure, if you are interested in further online trainings, to sign up to the next ones. I think this is a great opportunity to get used to the program and learn it, and see all the hidden features and functions that you can use. And of course, our website also offers a lot of additional value. So you can find a lot of recorded webinars. You can find knowledge base articles that tell you something about how to use the program, but also about general civil engineering topics and modeling related specialties. Sorry for that. It's late. I cannot find the right words. Also, we have some nice tools like the GeoZone tools, where you can check the wind, snow, and seismic loads for specific locations. We have very extensive cross-section properties or libraries where you can find basically all the sections that we have in the program libraries online if you use it for your studies. A lot of models to download and to mess around with and take as template for your own structure. And of course, we are also, you can find a lot of our webinars not only on our website, but also on YouTube. So make sure to also visit our YouTube channel. And yeah, I would be happy if you would join in the next online trainings and listen to my colleagues when they explain more about RFEM and how to use it to your advantage. So with this being said, I want to like to thank you all for your attention. I know it's 3 hours are very long, and I sometimes stumbled about my own tongue, but I hope you still enjoyed it and learned something new. And I would be happy if you now leave the online training, you are asked to fill out a survey. I would be very happy if you leave a comment and also rate the training. And for this, you can, I think, give points where 1 point is very bad and 5 points would be very good. So just to give you information on how to use the scale, 1 bad, 5 good. Yeah, and I would like you all to answer that. That would be very helpful for us, and also leave your comments so we can improve for the next time. All right, so enjoy the rest of the evening, and goodbye to all of you.